Hello everyone, today we're going to talk about exponential growth and exponential decay, one of my favorite math topics because it's incredibly applicable to daily life. So before we get into examples and seeing how the functions operate, I'm going to start by just reviewing what an exponential equation is. So say we have y to the 2x and we have a little graph here. When you plot out this equation, it's going to look something like this, where as we progressively go in the x direction, the y increases more and more and more. And that's because when you're raising it to a power, you just have to multiply the prior number again by the base, 2 in this case. So when you multiply things repeatedly, they get bigger, faster, and faster. So if you ever see a graph like this, you can say instantly, hey, that's an exponential equation. And this would be growth in this case because it's going up, it's growing. But when we have decay, we might see a relationship more like this. And that's just exponential decay because it's decreasing. And it follows the same properties, where as you go farther on the right for the x, it decreases, but goes at a slower rate, which we can see. We got less and less movement in the y direction. So it's just opposite as growth. We're decreasing, but we're decreasing at a slower rate. So with that in mind, let's talk about the formal equations that we can use when it comes to exponential growth, and we'll look at decay as well. So for growth, we have y equals a times 1 plus r, and I'm going to put x here, but some people use t. So you might see t, and that's perfectly fine. That's just the variable they choose. I like to keep it simple with x and y because I like to be able to just plug it in a normal graph and not be too confused where the variables are coming from. Now, initially, at first glance, this equation seems very confusing, and that's understandable. Up to this point, you probably have not seen any crazy equations, but we're going to break this one down step by step and explain it. So we're going to call A the initial value. We're going to call R the rate, and X is time, or you can call it the input. Same thing, just how you kind of want to view it. So for these variables, let's talk about it. A is the initial value, so that's your starting point. And when you see these example problems, that idea will come together more and make more sense. When it comes to R, that is the rate, so that's your growth rate or decay rate, which we will see in two different examples. And rates, we will see as, let's give an example. If it's a 12%, you're going to have 0.12 is your R, okay? So it's not 12. You don't plug in 12. 12% is represented by a decimal, which is 0.12. Just like 5% would be 0.05, and we're not plugging in 5 for the rate. That's a common mistake when you're starting, and it's understandable. But when you look at how the equation is built and what we're looking to achieve, it's going to make more sense why you would rather use a decimal rather than whole numbers. And then this x, which we can just look as time or input, is kind of just self-explanatory. It's a time. It's how much you're just observing this relationship for and see how it changes throughout those inputs. So that might not make perfect sense at the beginning, and that's totally fine. But we're going to look at some examples and explain it further, and I think it'll come together then. So let's just separate all this up here, keep this equation in mind, and we're going to have an example. An example, we're going to talk about a rabbit population. And this rabbit population, so this group of rabbits, grows exponential growth at 9% every year. So year over year, you're going to have 9% more rabbits in this example of a population. And to start, we're going to have 100 rabbits. And what we're looking for this one is a population at 15 years in. So let's go over this and just kind of state our variables that we can get from this. So growing at 9% every year, we know this is going to be the R. Starting at 100 rabbits, that would be the A, the initial value. And 15 years, that's our time or the input that we're looking to use, which we mark as x in the equation up here. So using these numbers, we're going to plug them into our equation and see what comes out. So we have y, which is what we're looking for, equals a, which we stated is 100 rabbits to start, 1 plus a rate of 9%, which is 0.09. And then for x, we have 15 years, as that's what we're looking for as our input. So, especially if you haven't done too much up to this point, you have to be careful with the parentheses when you're putting it in your calculator so you get the correct answer. So let's have 100 times parentheses 1 plus 0.09 is 1.09 end parentheses. And then we're going to raise that to the 15th power. Okay. And now if you're having issues, maybe you want to surround this 1.09 to the 15th power in another set of parentheses if your calculator is messing up. But hopefully when you enter this, you'll get an answer of 364.24. So let's write that here. And whenever you come to these kind of problems, it's a little confusing because you can't have 0.24 rabbits. So our best way of just working with this is round down. And we can say that about equals, squiggly equal sign for saying about, 364 rabbits. So that is interesting to look at because if we draw this in a graph, we can see that we're starting, let's say this is 100 here. But over the course of 15 years, we're going to get all the way up to 360. Which, it's not a linear relationship, so we can assume it probably looks something like that for the population. So as the rabbits have more and more time undisturbed to grow, they're going to grow at a faster and faster population, and eventually there's going to be a bunch of them. Which that's the idea of exponential growth. Given how much time, how much of something will we have, basically. So knowing exponential growth, now let's look at exponential decay, which is its brother in crime. They're very similar to each other, and you will see that in the equation. So for growth, we stated in the equation that y equals a times 1 plus r to the x. And now decay is very similar, and we will have y equals a to the 1 minus r to the x. So we have the difference here of the addition sign and the subtraction sign. If you ever have a trouble remembering which is which, growth, you know that you're adding things up, so plus. Decay, you know that you're taking things away, so minus. A little shortcut there. And now everything follows the same here. A is initial, r is the rate, x is the time or input. But let's look at an example because it's going to come off just a little different, and sometimes it takes your head a minute to wrap around. So let's see for this example. Say that we have a car, and the car value, say you're buying a brand new car. The car value starts at $5,000, quite cheap for a brand new car. But then we are given the fact that it loses 12% in value per year. So every year that you own this car, it's said to lose 12% of its initial value. And then we're going to look for the value after 5 years. Okay, so we're going to plug all of these variables into our new equation, but first let's say what's what. We know 5,000 is what the car value starts at, so it's initial value. We'll call that A. Loses 12%, which is our rate of change, our rate, which is R. And then we're looking for the value after 5 years, which is the time or the input of the equation, which is X. So let's write out our decay equation. We have y equals a times 1 minus r to the x. And we're looking for y, so keep that. We said the initial value is 5,000. Multiply that by 1 minus the rate, which is 12%. And we stated that we represent percents as decimals, so 0.12, that's 12%. And we're looking for the value after 5 years, which would be the input of this equation. So with all these in mind, let's plug this into our calculator and see what we can get as a result. So plugging this into our calculator, we have 5,000 times parentheses, and we'll just put this all out, minus 1 minus 0.12, which is also 0.88. You could just put that in. And we're going to bring that to the power of 5 for 5 years that we're looking of depreciation, how long it's losing its value. And we'll plug that in, and what we get is 2,638. So what we're saying is that after 5 years of losing its value, or in a lot of these cases we're going to use the word depreciation, where a car is going to be worth $2,638, which is almost half of its initial worth. So this is an example where you would use it in your real life. You could see how much value on average a car will lose, and then you could calculate that to see, hey, do I want to spend that much money if it's going to depreciate in this amount of time? Which case-to-case basis, all up to you, but it is great to know how to use these kind of equations because it simplifies things, and instead of hiring someone and paying someone else to do it for you, now you can do it because you are a pro mathematician. So next one, we're going to look at a growth example, and I'm going to give you guys a bit of a harder one just so you're not kind of shocked when you see these things on a test. So let's talk about bacteria, germs, things that grow over time as they're unbothered by contact. And we're going to say they double every 30 minutes. And we're going to start at 1,000 bacteria. Kind of hard to imagine, but let's just say we have 1,000 bacteria cells that we're starting with. And then we want to know how many after 2 hours. Okay, so as I recommend with all of these, first we're going to look at growth or decay. It's stated growth, which helps us definitely, but we can see that it doubles, so it's growing over time, so it's exponential growth. We know the equation for exponential growth is the following. Okay. Now, after that, I'd recommend looking for your variables that you want to put in the equation. So here we have double every 30 minutes, and that's where I kind of want to throw you guys for a little bit of a loop because you might see this, and it might throw you if you're just not quite ready for it. So we're going to ignore the 30 minutes to start with, but we're going to see double. Double is 100%, okay? You just know that you're going to have 100% more of what you started with, which is 2 times your initial doubling. So doubling is an important thing just to have in your mind right away, that it is just 100%. So that's our rate. We're going to start with 1,000 bacteria, which is A. And now we want to know how many bacteria will there be after 2 hours. And this is where it gets confusing, or where the 30 minutes comes in play. So let's bring hours into blend of minutes. So 2 times 60 is 120 minutes in 2 hours, which we know that's correct. So we're going to see how much time that we give these bacteria to grow. So we know they double every 30 minutes, so we have 120 minutes to work with, and we're going to divide that by 30. We'll see that they have the chance to double 4 times, because 4 times 30 minutes is 120, and that's 2 hours, which is what we're asked to look for. So you're looking at the time that you want to calculate for divided by the time that it takes to grow. And normally we speak in terms of it'll grow 8% every year and how many after 5 years, just to keep that consistent, but you don't always have consistency. You might have examples like this where they double every 30 minutes. How many do you have after 2 hours? So with all this information in mind, we're ready to solve the problem. So we said for A, it's 1,000, and that's because that's the amount of bacteria we're starting with. And then we have 1 plus the rate of growth, which is 100%, which is also 1. And then for X, the amount of time that we're looking to grow, we stated that's 4. because they double every 30 minutes, and there's 4 sets of 30 minutes in 2 hours. So we're going to plug this in our calculator and see what it gives us as an answer. So let's say we have 1,000 times parentheses 1 plus 1. You could just put 2. Definitely just exemplifying it in this case. To the 4th power, because that's growing for 4 times. And what we got as an answer is 16,000. And then we'll say bacteria as our unit. And this does make sense. We can write this out. The math isn't too difficult. Say we start at 1,000, and then we'll have 2,000, 4,000, 8,000, 16,000. So that's 1 time doubling, 2 times doubling, 3, and 4, which lines up with our answer. So that's a little bit of a harder example, and if you guys are just starting with this topic, probably as hard as it will get. So if you can do that, I feel pretty confident about your ability. But just look that over, try to get your mind around the idea of rate and time and how they work with each other. So we're going to have another growth example here. If you can do growth problems, you can do decay problems. They're the same thing. They're just worded slightly differently. Go back to the car example if you get confused when it comes to decay. So for this growth example, we're going to say we have sheep, a sheep population, and we're going to start at 200. And every year they grow 10%. So grow 10% per year. And then we want to know when will population be at 500 sheep. Okay, now if you're seeing this, you already know right away something is different. We're trying to figure out where the population will be at, and that's incredibly different than just plugging everything in. But still, with that in mind, I would like just to remind ourselves of the equation we're using and to name some of our variables that we do know from this. So we know to start, we have 200 sheep. That's our initial value. Grow at 10%. That's the rate. What will the population be at 500? Now that's a little different, but we know that when we say after growing for a certain amount of time, we'll be at a certain value. And that's why we set y equal to everything, because that's our output. So when will the population be at something? That's our y value in this case. Okay, so let's plug all that in and then just look at it, talk about it, and think about how we might be able to figure this out. So 500 equals A, which is 200, times 1 plus R, which is 10%, 0.10. And then we're going to have that for X amount of time, which isn't stated. So this is what's different. Now we have to find X instead of going for Y. Okay. So with that in mind, we're going to move around some values and make this a little easier for ourselves. So first, let's divide by 200 to get that out of the way of the problem. So 500 divided by 200 is 2.5. And that's going to be equal to what's left over, to X. Okay, now here is where you have to know how to use logarithms. And if you haven't, I'll make a video and it'll explain it, but it's not as complicated as it may seem. We need to solve for X to figure out how long, how much time we have to put in to get to that 500 population. So what we're going to do is we're going to take the log of both sides, okay? So we're going to say the log of 2.5 equal to the log of the right side, which we said is 1 plus 0.10 to the X. This is also 1.1 right here. Same thing. Okay, and now with this, we're going to actually do the logarithm, and then we'll be able to solve. So that might sound confusing if you haven't done a log. Well, let's see what that looks like. So we can still say log of 2.5 is log of 2.5. But when we take the log of 1.1 to the X, we're going to have X times the log of 1.1, which this is just how logarithms work. I'll write it out here. So we have log of 1.1 to the X The x comes in front of the log, and then we keep the value that was being exponentialized. So we have x times the log of 1.1. And I'll make a video about logs, kind of explain this more in detail, but they are needed for these kind of problems to be able to solve them. So finishing with the algebra, we have log of 2.5 equals x times the log of 1.1. Now to get x by itself, we're going to have to divide each side by a log of 1.1. So on the left side, we have log of 2.5. Divide that by log of 1.1. And that's all we have to do to find x. And your teachers, if they're not letting you use a calculator, which would be interesting, they might just be fine with this. And nothing's wrong with this as an answer, but it might help us if we can put in our calculator and see what actually comes out on the other end. Okay. So we're going to have log of 2.5 end parentheses, and divide that by the log of 1.1. Okay, now plugging this in, we're going to get 9.61. So let's write that out, 9.61. Now what did we find? The question which we were solving is, when will the population be at 500 sheep? And we started at 200. Now we used the growth rate of every year. So we were talking about growth over the terms of year, because it grew 10% every year. And this is where the idea of the bacteria and having your rate consistent with your time or your input is important, because right now we're talking in the terms of years. So our 9.61 is years. So 9.61 years, 9 years and however many days in the 200s probably, is how long it takes from our sheep population to go from 200 all the way to 500 at a growth rate of 10% every year. So that's all there is to exponential growth and decay for the most part. There are some harder problems like these last two that we can see, but I wanted to give you guys an example so you'd be ready if you saw them on your test. But at the basic level, a lot of it is just plug in the variables and see what comes out the other end. And sometimes, in the case of logarithms, you're going to have a value you're looking for, and you have to use logarithms to move some of those variables around and then solve for it with algebra. So all I recommend is over time practice and practice more with these. You'll become comfortable, and after a while you'll see that a lot of them are the same thing, just appearing different. Thank you for tuning into this one. I hope the video was helpful. Share it with your friends, like, comment any questions. I'll be more than glad to help, especially because I know this topic is confusing.